Y is an exponential random variable with a parameter mu. Those came right off of the chalkboard. Then Billy wrote this routine called Q, and here are its parameters. The first parameter is the distribution of the time between arrivals to the queue. The second parameter is the distribution of the service time at the queue. The 4 here tells us we're interested in the 4th customer's sojourn time. The 0 tells us that we started with 0 customers in the system because we said it was empty. And the 1 here tells us that there is 1 server. Okay? So he wrote that, and we not only want the distribution of that 4th customer's sojourn time, we want its mean, and we want its variance. Any questions just generally over the code? Now there's a lot of details behind the scenes here, of course, to do that. Okay. On the next page, there's the scoop. Here is the probability density function of the 4th customer's sojourn time, symbolically in terms of lambda and mu. Okay? And why is it so long? It's so long because you've got to consider all of those things that can happen with the first 3 customers. The mean of this random variable is this awful expression right there, and its variance is that even more awful expression down there. Any questions? The next example. Calculate the mean, variance, skewness, kurtosis of the initial customer sojourn times for an MM1Q with lambda equals 1. Notice we're now putting in numbers rather than symbols. Mu is equal to 2, and k equals 0, 4, or 8 customers initially present. And there's the code. It's not very interesting. X is exponential 1, Y is exponential 2. We're going to run from 2 all the way out to 60 customers. We're going to call Billy's Q routine and then print out the values. Okay? The more interesting thing is to look at what happens. This is the mean sojourn time, and notice what happens. When you start out with k equals 0 customers, that is empty and idle, this thing comes up to a steady state value. But when you load that system up with 8 customers, it starts out much higher, but then eventually comes down to a value. And I think we cut it off at 1%. When they were all within 1% of the theoretical value, we put a little line in there, and we said, you need 36 customers to warm it up with respect to the mean. But with respect to the standard deviation of the sojourn time, here it is empty and idle, 4 customers initially present, 8 customers initially present. It takes you 46 customers to line it up, to warm it up with respect to the standard deviation of the sojourn time. And so it goes. Here is the skewness, and here is the kurtosis, right? And it takes you 50 to warm up the skewness and 56 to warm up the kurtosis. So what we're seeing here is verified by Monte Carlo simulations. That is about how long it takes to warm things up and get them within 1% of their theoretical values. Okay. Now, let me go on to another bit from queuing that Billy did, and that is find the variance-covariance matrix of the first 3 customer sojourn times in an empty and idle MM1Q with arrival rate lambda and service rate mu. So let's assume that, let's go with U3 here. These are the first 3 customers, okay, that are in the queue. If that's the case, what do we have? We've got, well, let me ask you this. Are the 2, you have a sojourn time and Grace Ann has a sojourn time. Are those 2 sojourn times independent? I got 2 no's. How come you're saying no? You're right.
The amount of time it takes to process the first person will be added to the second person's time.
Exactly. If Grace Ann happens to enter and there's a line, right, then your sojourn time will be correlated with hers and likewise, right? So these are not, these sojourn times, which I'm calling here T1, T2, and T3, those are the sojourn times for the 3 of you. Those are not independent random variables, are they? So that means because they're dependent, they have a variance-covariance matrix, and this was the next problem that Billy worked on. So here is the transition diagram, and I got a little bit of a pointer here. That's not much of a pointer, but hopefully you can see it. When we start right here, this is the beginning of the simulation, and we're starting out empty and idle. And the first thing we always have is an arrival. Now, once we have that arrival, what can happen next? Now you have two possibilities. You can either have another arrival, or what else could you have going down this way? You could have a departure before the next arrival. So there's two things that are competing for the next event. And it turns out that anywhere in this triangle right here, you have the possibility of moving either this way or moving this way. For any of those three dots, you have the choice of either going here or here. Now, if we're only looking at the first three customers, then you have arrival, 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 and you're not looking at a fourth customer. You got to have departure, departure, departure at that point, right? We just don't even think about the fourth customer that's going to come in. It turns out the number of paths through this particular number is the Catalan number, and it's 2n factorial divided by n factorial n plus 1 factorial. So in this particular case, Billy wrote the routine that gives the covariance between the first and the second customer's sojourn times when n equals 3, and here it is, the covariance between the first and second customer's sojourn times when there are 3 present, and what he got for that was, he got this quantity right here, which is the 1, 2 element of the matrix. And so on it goes. We filled in all the elements, and there they are. That's as much as we could fit in. That's why we only had 3 customers, is you get a matrix that looks like that. So let's run through it. I don't know if you guys know much about variance-covariance matrices, but on the diagonal are the variance terms, and then on the off diagonals are the covariance terms. So this one we can actually think about, all right? The first customer, you were the first customer, right? And what's your name? Eve. Okay. So she is lucky in some ways. In what ways? She will always arrive to a what? Empty and idle system. So how long will it take her to get through? Just the service time. She doesn't have any queuing time, right? So if she just has service time, what is the variance of the service time? 1 over mu squared, right? It is the variance of an exponential random variable with rate mu, and so that's what you get right here. So there is her service, the variance of her service time. What is this one right here, the 2, 2 element? That's going to be the variance of the second customer's sojourn time, and this is the variance of the third customer's sojourn time. Now how about this one up here? That is the 1, 2 element of the matrix, so that is the covariance between those 2 sojourn times. All right. If you want to put in some numbers, for example, lambda equals 1 and mu equals 2, you get this matrix, which is the same as that. And I put the dots in there so it didn't, I didn't have to bring the font size. It's a symmetric positive definite matrix. Okay? And then we ran it, and we said, let's get the first 9 customers, see if we can do the variance-covariance matrix of the first 9. This was surprisingly, this took a lot of CPU time when we did it, because to get the first 9 customers, you've got to consider all of the things that can happen, right? All of the paths through that network that I showed you before, right? The little triangular network, and that's a lot of paths going through there. You calculate the probability for each one, and then you kind of pile these probabilities on top of one another. And when you do that, there's the answer. I don't know if you probably can't see that from the back, but it's some horrible numbers there. But those are exact, and we confirmed them by Monte Carlo simulation. But that is the variance-covariance matrix for the first 9 customers in an initially idle MM1 queue with those service and arrival rates. Oh, 6 minutes. We're going to make it, but we got to go fast. Here's the last one. Testing random numbers. This was Matt Duggan again, same guy that did the stochastic activity networks. It turned out some very, very smart people, Metropolis and Van Neumann, from way back, were working on something called random numbers. They knew that that was important. If we can get numbers that look like they are falling between 0 and 1, that's a good thing. They didn't solve it. They had a lot of different ways of trying, but they didn't solve it. But in 1951, Leemis pretty much solved the problem. And his generator and others like it have been used for years. But basically what it does is it says you pick a very, very large number here, a large integer m here, and a large multiplier here, and if you take a string of integers and put them through this recursive definition, you eventually get uniform 0, 1s by using this formula. They will be between 0 and 1, and they will kind of jump around and look like they're uniformly distributed between 0 and 1. Here was Marsalia's observation from 1968. Random numbers fall mainly in the plane. That was the title of his article, and it's one of the best titles of an article ever. Does anybody know anybody an old movie buff that knows why that's a clever title? Yes, Grace Ann.
My Fair Lady.
My Fair Lady. And what's the song from My Fair Lady?
The rain in Spain falls mainly in the plain.
Yeah. Okay. So the rain in Spain falls mainly in the plain, and so he took off on that. And here's what he noticed. And by the way, one of the worst generators. I hope none of you are going to take a position with IBM here. Anybody got a job offer with IBM? Good, because they created one of the worst generators out there, Randu. It broke all the rules. But basically, here's the idea. You would like to have adjacent uniforms kind of filling up the whole square, falling randomly, wouldn't you? Right? If I have a string of uniform 0, 1s, I would like to have them fill up the unit square. Well, it turns out they don't do that. Here's what they do. They fall in these lines. And in 3 dimensions, they fall in planes, right? Mainly in the planes. That's where the clever title came from. This is bad. These don't look uniform, do they? If I'm running a simulation and I need this little box up here to represent maybe a nuclear reactor that has a meltdown, I'm never going to get anything up there, and that's bad. We want them to fill up the whole box, and instead they're sitting there in these lines. But what Matt and I looked at was we looked at the order that they fall in here. Not only do they fall in these lines, if they're going in this pattern right here, that's even worse still, isn't it? Because now they have a pattern. If I took those same numbers and right here are the same exact dots, but if the order that they came out was like this, it was kind of like just a mess, that would be more random than this, wouldn't it? So what Matt and I tried to do was determine the distribution from one point, the distribution of the distance from one point to its successor. Everybody see what we're up to? Okay. So let me go fast because time is short. So we want to find the distribution of the distance between 2 random points in a unit square, and that's capital D. That's a random variable. Now remember, all of these guys right here are uniform 0, 1s, aren't they? So this is a good application for Apple. And the code is right here. U1 and U2 are both uniform, so we take the difference of the 2 of them. That gives you this. And then what do? We square that, and then we transform that difference. We add 2 of those up. That's the plus right here. And the last step is to take the square root. And right here, Apple has determined if I have 2 points in the unit square, what should be the distribution of the distance between them. Now tell me how close those points could be if they were really uniform. 0, right? They could be right next to each other. How far apart could they be?
Square root 2.
Square root 2, right? They could be at opposite ends of the square. So when we put that into Apple, it comes back with this distribution, not too bad, just a polynomial between 0 and 1, but for some reason between 1 and the square root of 2 you get square roots and arc sines and all kinds of nonsense. But that right there is the distribution of the distance between 2 points in the unit square. And if you want to see what that looks like, it's kind of a hump-shaped thing. Not many are right next to each other. Goes up, peaks here somewhere around 0.4, comes down. And you can see at 1, it kind of changes shape from this hump shape here into this tail. And this is ending out here at exactly 1.414, the square root of 2. And we have 1 minute left. Here's the end. Apple is free. If you want a copy, just knock on my door and I'll email it to you. It's no big deal. Easy to use, gives exact solutions to sometimes nasty probability problems, and I'm always looking for application areas. So if today's talk has triggered something in your mind, you say, could Apple be used for this? I'm always very interested in hearing of new applications. And you've seen 4 of them here, but I've got 10 or 12 that I think are pretty good applications. And that's it. Do you guys have any questions or anything? Okay, yes?
What's Apple written in?
It's Maple based. So Maple is doing all that heavy lifting. So remember on the previous page when you saw that arc sign down there? All of that, the reason it does things exactly is it's doing the symbolic manipulations. And we didn't want to get into arc signs and all that business. All right.
I was wondering how much slower is using algebra to solve these problems rather than just the